Hello everyone, welcome back to part 2 of chapter 29. In the first video for this chapter we saw how we could take a wire with some current running through it and derive the magnetic field in an area close to that wire. And specifically we saw the expression for magnetic field produced by a straight wire and magnetic field produced by a curved portion of wire. So now what we want to do with that information, we're going to take the magnetic field expression for the straight wire, which, just to review, is mu naught I over 2 pi r. And mu naught is the new permittivity for magnetic systems. And we don't want to make the mistake of getting this confused with just regular mu, which is the dipole moment for a magnetic coil. This was actually defined in the previous chapter as NIA. And so based on the current, the cross-sectional area, and the number of loops that you have in a given coil, the magnetic moment would then be NIA. And we could then apply that to information like the torque that would be involved with that particular coil, and also things like potential energy associated with that coil. So we want to make sure we don't get those two mixed up, but we'll always know the difference between the two because mu naught will have the zero attached with it, and this is just a constant value of 4 pi 10 to the minus 7, whereas this can vary based on the coil and the number of turns and, of course, the current that's in the system. So with that said, let's take the magnitude of the magnetic field that a wire is producing, and let's go back and revisit a previous problem. If you'll remember, we did a problem where there was a wire carrying a certain amount of current, and that wire was exposed to an external magnetic field. And from there, we could take our force expression, F equals IL cross B, and we could determine not only the magnitude of force that acts on the wire, but also the direction that that force is going to point based on the right-hand rule. What we didn't do in that previous problem is we did not explain where that external magnetic field came from. In this example problem, we will do that. And the way we're going to explain where that external magnetic field comes from is we will introduce a second wire. And this second wire will have its own unique current running through it. So we'll go ahead and specify the difference between the two current values. We'll let the wires run parallel, and the currents can run in the same direction up. But in some future examples, we can change the orientation of the wires, the direction of the current, etc. And since we know that a wire carrying current will produce a magnetic field, that means that both wires will produce magnetic fields. The magnetic field that is produced by wire 1 will affect wire 2. And while that's happening, the magnetic field that wire 2 produces will affect wire 1. So let's find out the direction that those magnetic fields should be pointing. If we go back to the right hand rule, the straight portion of the diagram will be our thumb. The curved portion of the diagram will be the curve of our fingers. Now in this diagram, the straight portion of the diagram is the currents. We have current 1 and current 2. They're running in a straight line. And so the magnetic fields that are associated with each wire will be curving around those wires. So in the case of wire 1, I'm going to use blue for this. We need to point our thumb in the direction of the current. So we're going to point our thumb up. And then our fingers will curve around the back of the wire and across the front of the wire. And so that magnetic field is going to orbit around the first wire. Likewise, and I'll use red for this one, wire 2 has current pointing up. That's the straight portion. We'll point our thumb up, and we will see the curve of our fingers also traveling around wire 2. And so we have field 2 orbiting around wire 2. Field 1 is not going to affect wire 1. But if we extend field 1 out further, remember that the field lines themselves are not just going to be at one fixed value. As we travel further and further away from the wire, the magnetic field will depend on that separation distance. And what I want to do is I want to see what those magnetic field lines from wire 1 are going to look like when they get to a distance of r away from wire 1. In other terms, what happens when the magnetic field from wire 1 interacts with wire 2. Now, if you're following the curve of your fingers as you follow magnetic field 1, it will intercept wire 2 traveling into the board. And that's really the only part of magnetic field 1 that I need to see in this diagram, is how that magnetic field will interact with current 2. And that's because when I go to plug everything into my force equation, I need to know the angle relationship between the direction that current is traveling through that wire and the magnetic field that it has been exposed to. So we'll go ahead and get rid of all of these other magnetic field lines for field 1 because we don't need them in our picture anymore. But before we continue on, let's also consider what happens as the magnetic field lines from wire 2 branch out, and what happens when those field lines intercept wire 1. So if you follow the curve of your fingers around wire 2, when those field lines finally intercept wire 1, they are coming out of the board. And so we have field 2 interacting with wire 1, and field 2 has its orientation pointing out of the board at that specific location. All right, so we are now set up and ready to look at the forces that are going to act on each of these wires. We need to be careful with our subscripts here. The first force that we want to look at the magnetic force on wire 1 as a result of wire 2. And so our force expression says IL cross B. All right, well, which current are we talking about? And which field are we talking about? Well, we want the force that acts on wire 1, and wire 1 has current 1 passing through it. L, the vector L, is the length vector that is associated with wire 1. But in our previous discussions and videos, we said that since current can't be a vector, we will assign the direction of the current to the length vector itself. So whatever direction the current is pointing, that's the direction that the L vector has to point. And then wire 1 is going to come under the influence of magnetic field 2. So from there we can evaluate the cross product as the magnitude of each vector times the sine of the angle that exists between them. When we look at the L vector and the magnetic field vector, the L vector is pointing up, the magnetic field vector is pointing out of the page, and another use of the right-hand rule says that the first vector in your cross product is your index finger. The second vector in the cross product is your middle finger. And the resulting vector is your thumb. Well, the result that we want to get from this combination is the force vector. The first vector in the cross product is the L vector, so take your index finger and point it in the direction of L. Second vector in the cross product is the field vector, so while keeping your index finger pointing up in the direction of L, you need to rotate your wrist so that your middle finger can point up out of the screen. And then the only direction that you can point your thumb without hurting yourself is going to be to the right. And so that will be the direction of the magnetic force on wire 1 as a result of wire 2. We also have the magnitude of that force vector. We'll go ahead and clean this up. We have current 1. The length of wire 1 is just L. The magnitude of field 2 is B2. And then if you look at the direction that L is pointing versus the direction that B2 is pointing, they are at 90 degrees with respect to each other. And sine of 90 is 1. So there we have it. There is the magnetic force acting on wire 1 as a result of being within close proximity to wire 2. Now that we have that, let's find the magnetic force acting on wire 2 as a result of being close to wire 1. Again, we'll set up our cross product, IL cross B, but this time we're talking about wire 2 being affected by field 1. The cross product for this will evaluate very similar to what we had for the last example. L for wire 2, I'm just going to assume that both of these wires have the same length. And so we can use the same L vector for both of those wires. But the direction that field 1 is pointing into the board. Our right-hand rule, again, says first vector is your index finger, so point your index finger up again. Second vector is the middle finger, so now we have to point our middle finger into the screen. And the resulting vector is the direction that our thumb needs to point. Well, in this case, our thumb ends up pointing to the left. And so there's the direction of the magnetic force on wire 2 as a result of wire 1. We'll clean this up a bit. And we get that the magnitude of this force is I2 LB1. And just like the previous case, the direction of our L vector and the direction of magnetic field 1 are also at 90 degrees with respect to each other. So our sign relationship just evaluates to a 1. And there's the force acting on wire 2. Now, we could leave it at this, but way back in Physics 1, there were some laws that were associated with moving objects, and all of those laws boiled down to the force interaction for those objects. And one of those laws said that if we had a force, that there needed to be an equal and opposite counterforce in the system. Well, why is there a force acting on wire 1? That force is a result of wire 1 interacting with wire 2. And at the same time, we have a force on wire 2 because it is interacting with wire 1. So that law of motion, which happens to be Newton's third law, says that for every force, we have to have an equal and opposite counterforce. Well, we've got the opposite thing going on. These two forces are pointing in opposite directions. And this is what we would call an attractive system. These two wires are going to be attracted to each other by those forces. But what about the equal magnitude part? Are these two forces, in fact, of equal magnitudes? And if we look at the two expressions, we have I1LB2 and we have I2LB1. Well, they look really similar, but the subscripts are in the wrong spots. So can we say that these two expressions are equal to each other, or do we need to do a little more digging? And the responsible thing is to dig a little deeper into the math, but we're actually ready to do that, because for each wire, we can actually produce an expression for the magnitude of magnetic field that each wire is producing. So in the case of wire 1 is going to produce field 1 by using mu naught I1 and 2 pi r. Wire 2 is going to produce field 2 as mu naught I2 over 2 pi r. Those two expressions can then be substituted in to the force equations that we're using. So for the first equation, we have I1L, and then B2. We said B2 is all of this stuff, so I'm going to write that in there. Mu naught I2 over 2 pi r. And then for the other force, we have I2L B1. Well, the only thing I have to do is switch out the subscripts, and I have my answer. So are those two expressions equal to each other? And they are. Everything on the top is the same for each expression. Everything on the bottom is the same for each expression. And so the magnitudes of each of those forces are in fact equal and opposite to each other. And so the force that we see between these two wires is dependent on the amount of current that runs through each wire, the length of the wires. In this case, we had the common length of L, and then the separation distance between those wires is R in this case. But this is just the magnitude of the force. Keep in mind the direction of the force came from the use of our right-hand rule. So what we want to do next is we want to consider what would happen in this system if we reversed one of the currents. And just so we don't get ourselves too confused by trying to erase and replace things, we'll just start from scratch with our diagram. We'll go ahead and keep current 1 traveling up through the length of the wire. We'll keep the same separation distance of R between the wires, but we'll have current 2 travel in the opposite direction. Now, when we do this, when we flip current 2 over, how is that going to affect the system? Is flipping current 2 over going to change the magnitudes of either magnetic field? And the answer should be no. The magnitudes of the magnetic fields that each wire produces are still going to be the same as what they were before. The only difference is what direction those fields are going to point. Now, wire 1, we haven't done anything to change wire 1, and so we should still see wire 1 with its magnetic field oriented into the page. So that's not going to change. But wire 2 has had its current flip over. We need to point our thumb in the direction of current 2 and allow our fingers to wrap around wire 2 and watch the curvature of your fingers. When your fingers curve around and they intersect with wire 1, well, your fingers should be curving into the page. And so field 2 is also going to be pointing into the page. How is this going to affect the forces? Well, let's take a look. The force on wire 1 as a result of wire 2 is IL cross B. Again, we're talking about wire 1 under the effects of field 2. The length of the two wires is still the same as what it was. So L is pointing up for wire 1. Field 2 is pointing into the board. Using our right-hand rule, index finger for L, middle finger for B2, thumb for force. In this case, our thumb needs to be pointing to the left. We have our index finger pointing up in the direction of L, Our middle finger points into the page. The only direction that our thumb can point is to the right. But now we evaluate this cross product, and there is absolutely no difference in how this cross product evaluates compared to the original diagram where our currents were running parallel to each other. We're getting the same magnitude for this force, it's just turned around. If we go through the same motions for wire 2 under the influence of wire 1, let's see here. Well, current 2 has now changed its direction, and our length vector has to be in the direction of the current. So by flipping over the current, we flipped over the L vector. L is the first vector in our cross product. That's your index finger, so point your index finger down. Your middle finger needs to be field 1. That needs to point into the page. So be careful not to strain your wrist as you move things around. But the resulting force that we get out of this arrangement has to point to the right. Oops. Get all the right subscripts in the right spot. So now we can see that these wires are repelling each other. This is a repulsive system as opposed to the attractive system that we saw up top. We'll go ahead and evaluate this force. We'll evaluate the cross product. We're going to get I2 LB1, sine of the angle between them. Well, the angle relationship between L and B in both of these cases is still 90 degrees. So we get I2 LB, 1, not 2, it should be a 1. And so the magnitudes of these two forces are no different from what we got in the previous case. And we've already done the work involved with substituting in the magnitudes of the magnetic fields. And so we will once again get the same equal and opposite force relationship between these two wires. Well, so why is this important? Why is it important to know if you're going to have some forces acting on your wires? Well, in the first case, up here, if your wires are being attracted to each other, those wires could bow in. And as those wires get closer together, the separation distance between the wires gets smaller. And as that happens, the magnetic fields that are being produced by each wire become stronger in their effects. And that's going to cause the magnetic forces on the wires to become stronger and stronger as the wires get closer and closer together. And one of two things could happen. One thing that could happen is that there could be so much force acting on one of these wires that it causes one of the wires to get ripped out of one of its connection points. And so you might set up a system of wires, turn on the current, and one of the wires rips itself out of the wall, essentially. But once that wire is disconnected, it no longer has current running through it, which means that there will no longer be any force relationship between those wires. So you come walking along and you see that there's this disconnected wire in the system. So you do the safe thing. You go and turn off all the power. You reconnect the wire. Then you go back to the circuit box. You flip the switch. to get some current running through it, and the wire rips itself out of the wall again. And then the wire doesn't have any current running through it, and so it just hangs there. The other wire is going to be standing straight like it's supposed to be, but this other wire is now ripped out of its port again. Another thing that could happen is if there's enough slack in these wires, the wires could end up physically touching. And once they do that, well, there's no more need for attractive force there. But if these wires don't have protective sheathing on them, you could end up with a short in the system. And so that could be just as bad. You could end up damaging sensitive components within your circuit if you did that. So what about the repulsive case? Well, in that case, we would see our wires bow outward. And as those wires get further apart from one another, the magnetic force acting on those wires would actually get weaker by the same argument. So I guess if you had to set up wires close to each other and minimize the amount of damage that you get having the currents run in opposite directions might be a better choice, but sometimes you don't have a choice. Sometimes you have to have current traveling in a certain direction, and the design of the circuit or the system may already be there, and you may not have an option. So how do you prevent a wire from ripping itself out of its connection port? Or how do you prevent those wires from touching and shorting out? And the easiest way to do that is to just place a piece of conduit around that wire. And it could be something as simple as a piece of PVC pipe. You could also use some kind of metallic pipe if you want. You just want to make sure that those wires are insulated if you're going to put them through a metal conduit. But this way, even though the wires are still going to have those force interactions between them, the force on the wires is probably not nearly strong enough to overcome the anchoring effects that those conduit pieces are going to provide. And a piece of PVC pipe, even a few feet long, is only going to cost you a couple of bucks at most. And it can save a lot of wear and tear on the system. Another thing to consider is that when it comes to a lot of our electrical systems, we don't just have direct current running through a lot of our electrical infrastructure. We have something called alternating current, and that is where the current effectively alternates back and forth in the wire. And if you have currents that are alternating their directions within these wires, you could very, very well have wires that are sort of dancing back and forth as the currents are switching back and forth. And that means that up here at your connection point, you basically have a wire that's wiggling back and forth, and it could eventually end up pinching the connection point and severing itself from the connector. And so that's an issue as well, but that can also be overcome by putting a piece of conduit around that wire and just preventing that wire from moving back and forth. So very, very simple engineering solutions to these kinds of things. Obviously don't want to go to your boss and recommend a complete redesign of the system when you can just as easily fix the problem using a $5 piece of PVC pipe. All right, so I think that is probably going to be enough for this video. This video is obviously a bit shorter than the others, but the next topic that I want to go to deals with something called Ampere's law. And Ampere's law is sort of synonymous with Gauss's law. And if you remember from chapter 23 with Gauss's law, we were able to evaluate electric field magnitudes by encasing electric charge in these imaginary containers that we called Gaussian surfaces. And so we want to see if we can use a similar approach like that with wires and current to figure out what the magnetic field in a system is going to be, and then we'll apply that approach to some other situations that the calculus derivations that we saw in the previous video might not be especially easy to do. So we'll see you back here for video 3.